Okay. The ampere. The ampere, symbol A, is the SI unit of electric current. It is defined by taking the fixed numerical value of the elementary charge, symbol E, to be 1.602176634 times 10 to the minus 20 to the minus 19th when expressed in the unit C, which is equal to AS, or when expressed in the unit coulomb, which is equal to ampere second, or the second is defined in terms of the cesium frequency. This definition implies the exact relation E equals 1.602176634 times 10 to the minus 19th ampere seconds. Inverting this relation gives an exact expression for the unit ampere in terms of the defining constants E and the cesium frequency. 1 ampere equals E over 1.602176634 times 10 to the minus 19th inverse seconds, which is equal to 1 ampere equals 1 ampere equals 1 over 9,192,631,770 times 1.602176634 times 10 to the minus 19 times the cesium frequency times the elementary charge is approximately 6.7896868 times 10 to the 8th times the cesium frequency times the elementary charge. The effect of this definition is that 1 ampere is the electric current corresponding to the flow of 1 divided by 1.602176634 times 10 to the minus 19th elementary charges per second. The previous definition of the ampere is based on the force between two current-carrying conductors and had the effect of fixing the value of the vacuum magnetic permeability mu sub 0, also known as the magnetic constant, to be exactly 4 pi times 10 to the minus 7th Henry's inverse meters equals 4 pi times 10 to the minus 7th Newton's inverse amperes squared, where H and N denote the coherent derived units Henry and Newton respectively. The new definition of the ampere fixes the value of E instead of mu 0. As a result, mu sub 0 must be determined experimentally. It also follows that since the vacuum electric permittivity epsilon sub 0, also known as the electric constant, the characteristic impedance of vacuum Z sub 0, and the admittance of vacuum Y sub 0 are equal to 1 over mu sub 0 C squared, mu sub 0 C, and 1 divided by mu sub 0 C, respectively. The values of epsilon sub 0, Z sub 0, and Y sub 0 must now also be determined experimentally and are affected by the same relative standard uncertainty as mu sub 0, and since C is exactly known. The product epsilon sub 0 mu sub 0 equals 1 divided by C squared, and the quotient Z sub 0 divided by mu sub 0 equals C remain exact. At the time of adopting the present definition, the ampere mu sub 0 was equal to 4 pi times 10 to the minus 7th Henrys per meter with a relative standard uncertainty of 2.3 times 10 to the minus 10th. The Kelvin. The Kelvin, symbol K, is the SI unit of a thermodynamic temperature. It is defined by taking the fixed numerical value of the Boltzmann constant K to be 1.380649 times 10 to the minus 23rd when expressed in the unit joules per Kelvin, which is equal to kilograms meters squared inverse second Kelvin inverse Kelvin, where the kilogram, meter, and second are defined in terms of the Planck constant, the speed of light, and the cesium frequency. This definition implies the exact relation K equals 1.380649 times 10 to the minus 23rd kilograms meters squared inverse second squared inverse Kelvin. Inverting this relation gives an exact expression for the Kelvin in terms of the defining constants, the Boltzmann constant, the Planck constant, and the cesium frequency. 1 Kelvin equals 1.380649 times 10 to the minus 23rd divided by the Boltzmann constant, kilograms meters squared inverse second squared, which is equal to 1 Kelvin equals 1.380649 times 10 to the minus 23rd over 6.62607015 times 10 to the minus 20 to the minus 34th times 9,192,631,770 times the cesium frequency. The Planck constant divided by the Boltzmann constant is approximately 2.2666653 times the cesium frequency, Planck constant, divided by the Boltzmann constant. The effect of this definition is that 1 Kelvin is equal to the change of thermodynamic temperature that results in a change of thermal energy kT by 1.380649 times 10 to the minus 23rd joules. The previous definition of the Kelvin said the temperature of the triple point of water, T sub TPW, to be exactly 273.16 Kelvin. Due to the fact that the present definition of the Kelvin fixes the numerical value of K instead of T sub TPW, the latter must now be determined experimentally. At the time of adopting the present definition, T sub TPW is equal to 273.16 Kelvin, where the relative standard uncertainty of 3.17 times 10 to the minus 7th based on temperatures of K made prior to the redefinition. As a result, the way temperature scales used to be defined, it remains common practice to express the thermodynamic temperature symbol T in terms of its difference from the reference temperature T sub 0 equals 273.15 Kelvin close to the ice point. This difference is called the Celsius temperature symbol T, which is defined by the quantity equation T equals T minus T0. The unit of Celsius temperature is the degree Celsius symbol degree Celsius, which is by definition equal magnitude to the unit Kelvin. A difference of interval of temperature may be expressed in Kelvin or in degrees Celsius, the numerical value of the temperature difference keeping this being the same in either case. However, the numerical value of the Celsius temperature expressed in degrees Celsius is related to the numerical value of the thermodynamic temperature expressed in Kelvin by the relation T divided by degrees Celsius equals T divided by Kelvin minus 273.15, section 5.41 for an explanation of the notation used here. The Kelvin and the degrees Celsius are also units of the International Temperature Scale of 1990, ITS 90 adopted by the CIPM in 1989, and Recommendation 5, CI 1989 PV 57-115. Note that the ITS 90 defines two quantities T sub 90 and big T sub 90 and little t sub 90, which are close approximations to the corresponding thermodynamic temperatures big T and lower t. Note that with the present definition, primary realizations of the Kelvin can in principle be established at any point of the temperature scale. The mole. The mole symbol MOL is the SI unit of amount of substance. 1 mole contains exactly 6.0221407 times 10 to the 23rd elementary entities. This number is the fixed numerical value of the Avogadro constant N sub A when expressed in the unit inverse mole and is called the Avogadro number. The amount of substance symbol N of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, or any other particle or specified group of particles. This definition implies the exact relation N sub A equals 6.0221407 times 10 to the 23rd mole, inverse moles. Inverting this relation gives an exact expression for the mole in terms of the defining constant N sub A. 1 mole equals 6.0221407 times 10 to the 23rd divided by the Avogadro constant. The effect of this definition is that the mole is the amount of substance of a system that contains 6.0221407 times 10 to the 23rd specified elementary entities. The previous definition of the mole fixed the value of the molar mass of carbon-12, the mass of carbon-12, to be exactly 0.12 kilograms per mole. According to the present definition, the molar mass of carbon-12 is no longer known exactly and must be determined experimentally. The value chosen for N sub A is such that at the time of adopting the present definition of the molar mass of carbon-12 is equal to 0.012 kilograms per mole, was equal to 0.012 kilograms per mole with a relative standard uncertainty of 4.5 times 10 to the minus 10th. The molar mass of any atom or molecule X may still be obtained from its relative atomic mass in the equation. The molar mass of X is the relative atomic mass of X times the molar mass of carbon-12 divided by 12 equals the relative atomic mass of X times m sub u, and the molar mass of any atom or molecule X is also related to the mass of the elementary entity lowercase m of X by the relation capital M of X equals n sub A of little m of X equals n sub A of the relative atomic mass of X times the lowercase m sub u. In these equations, capital M sub u is the molar mass constant equal to the molar mass of carbon-12 divided by 12, and m sub u is the unified atomic mass constant equal to the mass of the carbon-12 atom divided by 12. They are related to the Avogadro constant through the relation capital M sub u equals Avogadro constant times the mass little m sub u. In the name amount of substance, the word substance will typically be replaced by words to specify the substance concerned in any particular application. For example, amount of hydrogen chloride or amount of benzene. It is important to give a precise definition of the entity involved, as emphasized in the definition of the mole. This should preferably be by specifying the molecular or chemical formula of the material involved. Although the name amount has a more general dictionary definition, the abbreviation of the full name, amount of substance to amount, may be used for brevity. This also applies to derived quantities such as amount of substance concentration, which may simply be called amount concentration. In the field of clinical chemistry, the name amount of substance concentration is generally abbreviated to substance concentration. The candela. The candela, symbol CD, is the SI unit of luminous intensity in a given direction. It is defined by taking the fixed numerical value of the luminous efficacy of monochromatic radiation of frequency 540 times 10 to the 12th hertz. K sub CD to be 683 when expressed in the unit lumens per watt, which is equal to candelas times teridians divided by watts. Candelas, teridians, inverse kilograms, inverse meters squared, times seconds cubed, where the kilogram, meter, and second are defined in terms of hc, or the Planck constant, the speed of light, and the cesium frequency. This definition applies the exact relation. The monochromatic. This definition implies the exact relation of the luminous efficacy of monochromatic radiation is equal to 683 candelas, teridians, inverse kilograms, inverse meters squared, seconds cubed for monochromatic radiation of frequency V equals 540 times 10 to the 12th hertz. Inverting this relation gives an exact expression for the candela in terms of the defining constants K sub CD, H, and cesium frequency, or luminous efficacy of monochromatic radiation, the Planck constant, and the cesium frequency. One candela equals the luminous efficacy of monochromatic radiation divided by 683 times kilograms meters squared inverse seconds cubed inverse teridians, which is equal to 1 candela equals 1 divided by 6.626070015 times 10 to the minus 34 times 9,192,631,770 squared times 683 times the cesium frequency squared times the Planck constant times the luminous efficacy of monochromatic radiation is approximately 2.6148305 times 10 to the 10th times the Planck constant times the luminous efficacy time is approximately 2.6148305 times 10 to the 10th times the the cesium frequency squared times the Planck constant times the luminous efficacy of monochromatic radiation. The effect of this definition is that 1 candela is the luminous intensity in a given definition of a source that emits monochromatic radiation of frequency 540 times 10 to the 12th hertz and has a radiant intensity in that direction of 1 divided by 683 watts per teridian. The definition of this teridian is given below table 4. Okay, this is the end of section 2.3.1.